So when a system absorbs heat, its temperature goes up. And we call that delta T, and that would be the final minus the initial temperature. The increase in temperature is directly proportional to how much heat was absorbed. If you put more heat into the system, the temperature goes higher than if you put less heat in. So in order to make that into an equation, we need a proportionality constant. So that first statement, we can say that the increase in temperature, delta T, is proportional to the amount of heat. Or we can write that backwards. And in order to make this into an equality, we need a constant. So here we're just putting this constant in here to make it equal instead of just proportional. C here is called the heat capacity, and the units would be joules per degree Celsius or joules per Kelvin, because if we have units of joules per degree Celsius on our C times unit of degrees Celsius on our change in temperature, that gives us the unit of joule for heat. The units are going to work out. So the heat capacity is the heat required to change the temperature of a system by 1 degree. The larger the heat capacity is, the smaller the temperature rise will be for a given amount of heat that's put in. The heat capacity of an object depends on how much matter there is. Usually we measure that as the mass. So we say that heat capacity is an extensive property. It depends on how much there is. So if you're trying to make spaghetti and you're going to boil, say, 4 cups of water, or you have to make spaghetti for the varsity football team and you need to boil, how many would that be? Gallons and gallons and gallons. I've done that. Gallons and gallons. Those boys eat so much spaghetti. Which is going to take more heat to boil? The larger amount of water, right? That makes sense to us. So heat capacity, being an extensive property, isn't all that useful. So we make that into what we call specific heat capacity. And this is an intensive property. It's the intrinsic capacity of a substance to absorb heat. So heat capacity depends on amount of stuff. Specific heat capacity only depends on what the stuff is, not how much there is. So the specific heat capacity is the amount of heat needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. So this is going to have units of joules per gram degree Celsius. We can also talk about a molar heat capacity, and that's how much heat needed to raise the temperature of 1 mole by 1 degree. There you'd have units of joules per mole degrees Celsius. These are intensive properties like density and are much more useful. So the relationship here is that the heat is equal to the mass of the object times its specific heat capacity times the change in temperature. So this is nice, it's all spread out and it's all labeled and everything. But it comes down to this: Q equals MC delta T. Now technically this C is the specific heat capacity. It should have an S in it. The symbol for specific heat capacity is not universal. The units on this are joules per gram degree Celsius. You multiply that by grams and by degrees Celsius and you end up with joules. So that specific heat capacity is going to be different for each kind of substance. The only one you might remember would be for water. I need to fix this. Well, that's as small as it gets, huh? 4.184. I don't know why they rounded that. Specific heat capacity, these are in joules per gram degree Celsius. The specific heat capacity of pure water is 4.184 joules per gram degree Celsius. All of these other ones would be given to you. This is the same number as in that relationship between calories and joules. 1 calorie equals 4.184 joules. The calorie is defined as the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. So the specific heat capacity of water is 1 calorie per gram degree Celsius, which is equal to 4.184 joules per gram degree Celsius. This equation, MC, that delta kind of looks like an A, and so some students say Q equals MCAT to help themselves remember. The MCAT is a test you take for graduate school. Let's go back and look at this again real quick. So water, if we look at all these values here, which of these specific heat capacities is the largest? Water. And it's a lot bigger. Here's ethanol at 2.4, but the rest of these are all less than 1. Water has a very large specific heat capacity. And that is significant for our climate. So water can absorb a lot of heat energy with a small temperature change. If you have dry dirt and it's absorbing the same amount of energy, it's going to get hot much faster. It's going to get hotter. If you think about cold sand and dry sand in the sun, cold sand and dry sand, wet sand and dry sand, getting the same amount of energy from the sun, the wet sand is not going to be as hot, because the water absorbs the energy with a lower temperature change than something like sand that has a smaller heat capacity. So this is a picture of the Golden Gate Bridge over in San Francisco. San Francisco is on a peninsula, and it's surrounded by the ocean on one side and the San Francisco Bay on the other side. There's all this water around it. It is. It's beautiful. So the sun shines down and heats the air, heats the water, heats the land, heats the people, heats everything, right? Because there's this huge body of water, as it absorbs energy from the sun, the temperature only changes a little bit, whereas the temperature of dry land goes up much higher. And so the large amounts of water moderate the temperature that area experiences. Because then at night, when the sun goes down and we're not getting any energy, things start to cool down, but now the water is going to release thermal energy, because now the air is colder than the water. It's going to release thermal energy and moderate the lows. Here in the Central Valley, where we tend to have very low humidity and not a lot of water, not right now, but in the summer, we get these huge temperature fluctuations because there's very little water. At the coast, their temperature fluctuations are much, much less. Water is also commonly used as a coolant because it can absorb a lot of water. Water, oh gosh, it's about time to stop, isn't it? Water can absorb a lot of heat. And so it can be used to cool an engine, to move energy away from the engine, heat energy, so that it doesn't overheat. So let's see where we are. I'm going to save this example for Wednesday, because, I don't know, my talker is not working very well, and I don't think you want to see a complicated example like this right before an exam, right?